Hi, my name's Sean, and I work for SecureLinks, which is an Irish technology and consultancy company that specializes in delivering open source innovation and products. Some of our core area of expertise are high performance computing, artificial intelligence, and machine learning. I wanted to show you how, using only open source or otherwise free technologies, we can build a highly scalable, entirely web-based platform for your machine learning and artificial intelligence workloads. This sits on top of a traditional high-performance computing cluster with cloud bursting capabilities so that you can leverage cloud economics or the availability of accelerators in the cloud. What follows next is a shortened version of a talk we originally gave at the SUSECON conference 2020, where we showcased this technology in action with a demonstration.
So our background to this, we have many years experience working with HPC customers in that space, and we're on a journey with them to learn about and to move into the artificial intelligence, machine learning and data science area. So there's a lot of synergies between certainly the hardware and the methodologies that are available in HPC and AI, and our primary goal really is to bring that hardware along to work with HPC and AI platforms on top. So our base, as we said, is the ultra-stable SUSE Enterprise Linux for high-performance computing, which gives us all that support for GPU and CPU nodes and the interconnect and everything else that goes with HPC, as well as having support and available images on the cloud. So that's the base. On top of that, we layer what we are calling the AI stack, primarily for batch training, but also for AI inference type applications. So the visible part of this would be the Jupyter Notebooks application, which is really becoming, I think, quite rapidly the de facto standard in industry, the de facto way to develop, certainly for data science. We've chosen Python as the language here to talk about in detail and demonstrate, but that also works with Julia and R. So that's the top level. Underneath is a platform that's fully integrated with a standard set of these Python AI applications, such as TensorFlow. The whole premise throughout is that users can run an entire AI workflow entirely from the web. We're looking at bringing on board users who may not be familiar with Linux, unfortunately. The case is that we want to bring people up to speed and able to do AI applications without learning more than is absolutely necessary to run their workloads. Hybrid cloud bursting is also possible with the securing a hybrid cloud for HPC. This was an add-on to Slurm that Owen talked about in SUSECON 2019. So we see this stack really as a boarding ramp to AI. So we're really trying to reduce the barrier entry there and focus on people with AI and not Linux skills. For existing HPC experts who might be moving across into the AI machine learning, but we've made sure to include an out-of-the-box working AI stack of software as well. Throughout all of this, the development process, we've leveraged entirely throughout community building blocks, so free, open source if possible, or otherwise free software. So we do a small amount of work to create a platform, but we support a vast number of applications through that, as long as they work with Conda, Jupyter, or Singularity. To run through our use cases, our main use case there is to build this AI and machine learning technology alongside a traditional HPC customer. So we're looking at people, primarily even still, who are running an on-prem cluster and maybe having a small to medium sort of cloud workload and maybe a small add-on for AI on top of it, but they see that AI stack growing and becoming more dominant perhaps in the near to medium future. We're looking at targeting people who want to rapidly onboard new AI and machine learning users. So that might be new students in a university sector. It might be HPC familiar people in the oil and gas sector who are moving across to do more data analysis. They may have various experiences, but it may not be in the AI and machine learning space. And we wanted to make sure we can handhold them essentially as much as possible with this platform. The platform is fully supporting of GPUs, and with our choice of open source, I think this could be a low cost and flexible option versus the market to leverage either new technologies quickly or to take advantage of the cloud economics through bursting. So to go in a bit more detail on the solution, basically we were faced, when we were looking at this, we were faced with maybe the choice between two engines that sit underneath that were kind of on the face, perhaps roughly equivalent. So we weren't initially sure which way to go. The choice there was between batch and Kubernetes. We were seeing really the workloads more alongside the AI training were what people were looking at when we were initially scoping this. So AI training is probably more suited to batch workloads. Allows you to run these workloads and share alongside traditional HPC, given that that was the main target audience. And again, coupled with the existing skills, there's no need to skill up to use the Kubernetes. I'd say Kubernetes has its own merits as well, and I think Kubernetes would be really good if you're looking at real-time systems. So that would be, say, ingesting data from the Internet of Things and providing, say, an AI inference engine on top. So we've kind of focused on the training or batch inference, but I think this is a good low-cost solution to bring people into AI. So as an overview of the solution, sort of towards the right and the bottom there, you've got a diagram of your traditional HPC, a head node running Slurm. Underneath that, one or many traditional HPC compute nodes, their hardware, but also the ability to burst into the public cloud. So Azure is what we'll demonstrate. And then, so on top of this traditional HPC base that we've talked about there is just a Jupyter web node, which is fairly lightweight resource that can run also on the head node if your head node is reasonably well spec'd. And this is the interface that the users will see. This is how they configure batch jobs, AI batch jobs. This is how they configure their application. As far as the user is concerned, everything is available from that single pane of glass. People can talk through advantage and disadvantage of both types of clusters. So we've taken a hybrid HPC approach. So that gives you the ability to prove new technologies in the cloud and also to burst to the cloud if your workload is irregular. If we're trying to support these new hardware and accelerators, we need to be able to move quickly on the software front as well. I think it's difficult for anyone really to maintain absolute fully tested applications for AI as and when they come out. It takes time to really mature those and build them into something like SUSE Enterprise Linux or any of the other platforms that are out there. And we've seen this kind of in the field with our consultancy work, that you can provide a base core of very good and quality tested applications, which we do, but also people want to be able to bring in the newest version of TensorFlow, etc., very quickly as well. So we wanted to keep our platform very customizable so that people can bring in these applications, and we've given a set of tooling to support that. So to get a bit more technical now, I'll run through the proof of concept architecture and the look and feel of the graphical interface, and then some details around the choice of components we've used to build this up. So what's happening then, so when the users click spawn at the end of this only form that they need to kind of fill in to customize their job, Slurm will go away then and allocate a batch job according to their requirements. The only kind of fixed footprint there that is necessary is the head node itself and the Jupyter web node. Everything else potentially can be dynamic, either dynamically allocating a job from an existing pool of traditional HPC or completely dynamic in the sense that it's allocating a VM completely out of the ether in the cloud. So I talked about this, the stable core and then the user applications. So in the stable core, SUSE HPC, a Jupyter Hub web-based platform, a user-ready set of standard AI applications, and then the applications tooling as well. So the tooling to add new applications would be in our stable core. And then the glue, the SLES spawner for accelerated notebooks. This is the thing that connects your Jupyter Hub to the batch queues and allows you to spawn these Jupyter Hub backend instances. And of course, NVIDIA CUDA as well for GPU support. And then the user-ready stack. So this is the list of, let's call them core applications that are ready tested with the system. So this is a bunch of common Python AI applications, and we've tested that with Conda environments, with CUDA libraries, and then we've wanted to use containers as well. The AI ecosystem is absolutely filled with different containers that are freely available, let's say, on the web. So we need to be able to support that. We've used Singularity given the batch system kind of inheritance of this platform. So we've got Conda environments out of the box, we've got Singularity containers out of the box, and both of those have support for this list of standard Python applications. In the demonstration, I show you TensorFlow. So at this point, I will hand over to a demonstration of the work that we've done, and I'll show you all in action, running on Microsoft Azure, dynamically allocating GPU nodes from the cloud.
With that in mind, we've assumed that perhaps most of the CPU workloads can be run on traditional HPC that you have in-house, and maybe the GPU workloads are being outsourced to the cloud. So in our example here, we have a head node, which is also running Slurm and the Jupyter Web UI, and a cluster of CPU machines, in this case, just one. We've run these in Azure, just as an example. These could be running on-prem. Our dynamic resources are going to be allocated from Azure exclusively. When we log in, with the first thing the user is presented with is the spawner. This allows you to set up both the application environment and the type of system on which you want the notebook to run. So we're mapping system types to Slurm queues, and our dynamic cloud nodes are also a separate Slurm queue, just for the simplicity and ease of use. Select a few parameters like how long the job's going to be, how many CPUs you want, how many nodes and GPUs you want, and then the application environment under which it runs. So we've got two examples here. One, TensorFlow GPU, where we've used the Anaconda distribution to get our packages and libraries together. And one, Singularity environment, where we've used NVIDIA the NVIDIA Containers project and HPC Container Maker to build those containers. You don't need to use those technologies. Anything that works with a Singularity container and environment modules can be imported into this, as long as it supports Jupyter Hub. And even Docker containers can be converted to Singularity containers for the most part. Singularity is really the container technology that are optimized for HPC, which is why we've gone with that. So we're going to use one of our existing CPU nodes now to spawn a Jupyter Hub notebook environment. So what's happened there is we've submitted a batch job to the Slurm queue. That's gone away and it's allocated a node on the default partition, default queue, and then it's just dropped us into the user's home directory graphically. And I've got some demonstration notebooks to show you. So what we have right here is a typical notebook application where we import a lot of Python libraries and then we'll run some code. I'll just start it off. What we're actually running here is a neural network, a convolution neural network, to distinguish between different pictures and to categorize them into different groups. So we have the CFAR data set here of photographs of 10 different things, which are split into a test group of 50,000 images, a training group of 50,000 images, and a test group of 10,000 images. You can see they look a bit like this. It's the first 25 images of that group. We're going to set up the convolution algorithm in the next frames and then train that on the first 50,000 images using TensorFlow version 1.14. So this is running on a CPU node, and there are 10 epochs of the training, and it takes about 90 seconds for each epoch to run on our traditional CPU machine. If we leave that running, that's allocated from our CPU queue. If we leave that running and start a new job now from the control panel on our Jupyter Hub, we can add a number of servers. So each one of these is a different batch job that runs. I'm going to give it a name, GPU. And this time I'm going to run a cloud GPU node. So there's no GPU nodes running in Azure at the moment. Cloud GPU node, we ran TensorFlow GPU. We also have a Singularity instance installed. I'll run it in the Singularity instance just for a change. And allocate one GPU on the Azure GPU node, still running with one CPU core, and spawn that. Now this time, similar thing again, it's submitted a Slurm job, this time to the GPU queue, but there's no available GPU resources on the cluster. So what happens now is the SecureLinks hybrid cloud plugin for HPC kicks in, which we talked about in SUSECON 2019. This is going to go away now and allocate a new GPU node from the Azure pool in the cloud. That takes a few minutes to allocate and to spin up. The GUI will pause while it waits for the node to start. If I refresh now, it's allocated the virtual machine and now it's creating it. So that's going to take a few minutes just to give all the right OS settings to the machine and boot it up. And very shortly, so that's running, that means the OS is booted, the final settings are being configured and Jupyter starting, and will be redirected then to the user's home directory where we can start new applications. And we're presented with a very similar thing to what we were presented with on the CPU node, or the same thing. So in here, we've got a few more ready to go Python notebooks, all identical to the previous one, just to avoid running the same thing on multiple instances all at once. Import our modules, set up the convolution search algorithm, convolution neural network algorithm, and start training on 50,000 samples again. So just to jump back to the CPU job, we're still running. We've done about 4 minutes of training and we're on epoch number 4. On the GPU job, we're doing an epoch every 20 seconds. In fact, it speeds up through here. So this is actually going to overtake the CPU job, which means we can cloud burst when it suits us to take advantage of new applications and new accelerator technologies, and when CPU might actually be far too slow and costly. So in this case, we're using Singularity containers built through the NVIDIA Containers project and then customized using HPC Container Maker, which is also NVIDIA. The work we've done on that is to adapt the existing toolset by NVIDIA to work with SUSE. Previously, it only worked for Ubuntu and CentOS. So we can now build SUSE Leap containers using the HPC Container Maker. So we finished training the model, and we can make a few predictions based on that model. So we're going to use a few of the first few test images. So here we have the first 3 test images: a cat, a ship, and 2 ships. So our algorithm has predicted it's a cat, and it was a cat, and a ship, and so it's got it right for the first 2 instances. It's predicted this one to be an aeroplane, which is actually a ship. So it's got it wrong in the 3rd instance. So typically for these machine learning algorithms, you want to run on larger and larger training sets. So in our little example, whilst our CPU system is still running, it's probably going to finish in 15 minutes, not a big deal. But if we needed to train on millions of samples, the GPU thing is clearly the only way to go in a sensible time frame. So it's good to be able to cloud burst. So the next thing I'm going to show you, again, as I say, the machine learning AI space moves quickly, and it's important to be able to import and use new applications, techniques, or even just version updates to libraries. So there's no set list of applications in this portal that it works with. All we really have done is to provide the portal and an interface so that anything that can run Jupyter notebooks will be able to be integrated with this portal. On top of that, we've also added helper scripts to make sure that the most common ways to build an application on HPC in the HPC and AI space are well supported and easy to use with this portal. So somehow we have built an application. Either it's been deployed through Anaconda, which I'll show you in this case, which is a really easy way to install ready-built machine learning software. This is what we've done for TensorFlow. It's a few simple commands. Or we've downloaded or built a container either through the NVIDIA HPC Containers project, or just found a ready to go Docker application from the internet that works, and we've converted it to a Singularity image. So somehow we've got those applications. The ecosystem out there has a whole number of application sources that we just need to be able to download and use. There's very little need to rebuild everything yourself these days. But the final thing that's supported is, of course, standard environment modules. So we need to import this application that's installed. It's an upgrade to TensorFlow 2.1. We were running TensorFlow 1.14 before. We just give our app create a few parameters to tell it where the application is installed, where we might want to install an environment module for that application so that people can use a terminal to spawn out batch jobs if they wish, and give it a name to appear in our GUI. This is the app create script. This works for Conda and it works for Singularity, and it's probably the trivial example as it also works for environment modules too. So we've now just run that little command there that's added the environment module for Conda and pointed to the relevant version of the software and integrates it into our graphical interface. So now when we go back to our control panel, I'm going to stop this GPU server just to free up the resource. GPU 2.1. We can run on our new application, TensorFlow 2.1, which is running in a Conda environment. The SecureLinks hybrid cloud for HPC is configured to leave allocated nodes running for 5 minutes in this demo, so that GPU, even though it had no workload, didn't deallocate itself straight away. It would take 5 minutes. And now if we run the same benchmark and print out the TensorFlow version, it was running at 1.14. If we just run that cell now, we've installed an upgraded version of TensorFlow, and we're now running our new instance of our notebook in a different environment. Voila. As I say, we can do that also with Singularity containers as well. So that's it really. We've run a graphical web-based interface for machine learning and AI on top of a traditional HPC system. We've shown you how to cloud burst with the SecureLinks hybrid cloud for HPC, which you might want to do either to scale up for bursty workloads or to take advantage of new hardware accelerators that might be coming on stream. And I've shown you how to integrate applications built through traditional HPC methods and also through the methods that are very common and well used within the AI and machine learning space, that being containers and Anaconda. And so I hope you enjoyed the demo.
Thank you very much.